This unit covers Chapter 11 from your textbook. The objectives of this chapter is to investigate particle motion along the curved path using different coordinate systems, to solve for values of angular displacement, velocity, and acceleration using three equations of angular motion, and lastly, to distinguish between and calculate values of tangential acceleration, normal acceleration, and total acceleration. Angular displacement is the angle through which a point or line is rotated about a specific axis. The body can no longer be analyzed as a particle, since in circular motion it undergoes a changing velocity and acceleration at any time. Instead, consider the object as a rigid body. The distinction between displacement and distance is similar to that of rectilinear motion. Let's take a look at what I mean by analyzing figure 11.1, found on page 366. In this figure, we have a link that is attached to a base, and it's pinned at that base. So we are going to define 2 points on this body, this rigid body. We have point A, and we have point B. Point B rotates about point A, and it goes to 3 different positions. It starts at position 1, and it moves to position 2, and then again moves again up to position 3. That means it starts at the solid line, moves down to position 2 through an angle, we'll say theta, and then back up through an angle we'll call phi. That means that the displacement, remember displacement is the same in angular motion as it is in rectilinear motion, in that it is a vector, not a scalar. And so the displacement, say between points 1 to 3, would be phi minus theta, whereas the total angular distance traveled, so remember distance instead of displacement is just a scalar, so the angular distance between 1 to 3 would instead be theta plus phi. Angular displacement is typically measured in units of radians, or rads for short. 2 pi radians equals 1 revolution, which also equals 360 degrees. That means that we can use this in order to convert between these units. As an example, if we had 60 degrees, as we see below, and we wanted to convert that to radians or rads, we would take 60 degrees and multiply it by this conversion. So if we have degrees on top, we need degrees on bottom. So that's 360 degrees. For every 360 degrees, we have 2 pi radians. So if we take 60 times 2 pi divided by 360, we get 1.05 rads. Okay, and that's what is shown below here. Similarly, if we had, for example, 3.4 rads, and we wanted to convert this into revolutions, what do? We have to multiply, if we have rads on top, we have to multiply by rads on the bottom. So that's typically in terms of 2 pi. And for every 2 pi radians, there is 1 complete revolution. And so 3.4 times 1 divided by 2 pi gives us 0.54 revolutions. Okay, so that's how you would use these to be able to convert between those 3 units. So usually in terms of radians, degrees, or revolutions. Okay, so let's take a look at how we apply this to example 11.1 from the textbook. So in this example, it states that an ammeter needle starting from a 0 reading deflects 40 degrees clockwise and then returns 15 degrees clockwise to indicate a final reading, what is its angular displacement and angular distance in terms of radians? So really what this example is doing is taking into account the information that's provided on the last two slides. So that means we draw out the example that's given. We start with a rigid body that is located like this, where we have it at position 1, and then it moves to position 2, and then back up to position 3. 1 to 2 is a total of 40 degrees, and then 2 to 3 is a total of 15 degrees. So we need to determine what is the angular displacement and distance in rads. So our total displacement, call this theta, would be equal to 40 degrees minus 15 degrees, which is equal to 25 degrees. We need to convert this into radians, so we're going to multiply this. If we have degrees on top, we need degrees on bottom, so 360 degrees for every 2 pi rads. And so theta is equal to 0.437 rads. Now, as you may remember, displacement we called a vector, so we need a direction, right? We need a magnitude and a direction. So just by stating 0.437 rads is not enough. We need to know what direction. If it started at 1 and ends at 3, it's 0.437 rads in the clockwise direction. So we need to show it like such. And then either highlight, put a big red box around your final answer there. Similarly, our angular distance then is equal to 40 degrees. Now it's plus 15 degrees for a total of 55 degrees. And we're going to use the same conversion. So 360 degrees for every 2 pi rads. And that gives us 0.96 rads. And for this answer, we do not need to give it a direction since it is just a scalar that they are looking for. So next we have velocity. Similar to rectilinear velocity, our angular velocity is the rate of change of the displacement. In this case, it's of angular displacement. And so you'll notice that the equation looks very similar. We have the average angular velocity is defined as the angular displacement over time. So our angular velocity, or average angular velocity, is delta theta over delta t. So all we're doing is we are changing the symbols here to account for the fact that it is slightly different. Before we had v is equal to delta s over delta t. Remember, this is for our rectilinear motion. And now for angular motion, we have omega is equal to delta theta over delta t. Before we get to some practice problems on that, I'm just going to continue to angular acceleration. We're going to go through all of the remaining equations just because they align very well with rectilinear motion, which we've already looked at. And then we'll go through and just do a bunch of practice problems going through each of these equations. So for angular acceleration, this is the rate of change of angular velocity. Angular acceleration is defined as, this is alpha equal to delta omega over delta t. So this is very similar to our A is equal to delta V over delta t equation. Again, that one is for rectilinear motion. And you can see example 11.3 on page 367. Brings us to the three equations of angular motion. These align exactly with the three equations of linear motion. Okay? The only difference is you are interchanging the symbols for the angular values, their angular equivalents. So where theta is equal to omega naught t plus 1/2 alpha t squared, that would be equation 4 here. This aligns with our original equation 1, which is S is equal to V naught T plus 1/2 A T squared. So that was equation 1. Our equation 2 was V is equal to V naught plus AT times 2. And last, we have v squared equal to v naught squared plus 2as. There's equation 1, 2, 3 with the equivalents for angular motion, equations 4, 5, and 6. So please make sure you know what the equivalent values are, equivalent symbols are, going from linear motion to angular motion. I like to go ahead and show the next slide because that helps show the conversion between the two, which will be very, very helpful as we start going through these practice problems. So how do we convert between these linear and angular values? So your linear displacement, velocity, and acceleration to our angular displacement, velocity, and acceleration. You can see here that here's the conversion, and there is one common term between all of them. Okay, one common term, and that is the radius. Okay, how far from the point about which the body is rotating, that radius arm, that is the conversion between our linear and angular motion. So a feature common to all three equations is that rectilinear value equals the radius multiplied by the angular value. So as an example, we have a circle here and it's rotating about its center position. Okay, so it's rotating, and we'll say that it is rotating with an angular velocity, so that would be omega here. And we want to know what the linear velocity is as an example on this body. Well, the entire body is rotating at the same angular velocity, no matter what point you pick on this body. However, we're looking at an instantaneous linear velocity. We have to pick a point. So that point could be on the outside of the disc or the wheel, or it could be inside. What do I mean? I could say pick a point right here. We'll call this A, or I could pick a point, say over here, and this would be B. And at each of those points, instantaneously, I can decide I want to calculate the linear velocity at that point. And I can do that using the equation v is equal to r times omega. If I know that this entire body is rotating with a certain angular velocity, then all I have to do is figure out the radius arm. That is the point from where the body is rotating about. So that would be O in this figure here. That would be this center point. And then I draw a radius arm. So I'm going to do that. So to point A, there's RA. And then I draw a second one, and this is RB. So now I would be able to solve for VA is equal to RA times omega, and VB is equal to RB times omega. So I can figure out that instantaneous velocity at any point on that body, as long as I know the distance from its center of rotation and its angular velocity. The other important note to take here is the direction. You might say, well, it's a linear direction. What is the direction of velocity? Now, this is really, really important. The velocity always acts perpendicular to the radius arm. So for point A, since I know it's rotating clockwise, I know that velocity has to be going, obviously, some point to the right at exactly 90 degrees to that radius arm. So if I draw this out, it would look like this. That would be VA at 90 degrees. Similarly, at point B, its velocity would be right there. Okay, VB, 90 degrees to that radius arm at B. Okay, so there's a lot of information to take in. We are going to look at examples to see how we apply all of these equations and be able to convert between our linear and angular displacements, velocities, and accelerations. They all kind of work together here, just as we saw. So I want you to take a look at examples 11.6 and 11.7 on page 372. We're also going to work through together. We have 11.27, 11.40, 11.46, and 11:59. So the next video, I'm going to go through and do a number of practice problems that uses all of the equations that we've now seen on the last few slides. Okay, for the first practice problem, we're going to take a look at 11:17, which can be found on page 379 in your textbook. For this problem, it states that a flywheel accelerates for 8 seconds at 1.3 rads per second squared from a speed of 40 RPMs. Determine A, the total number of revolutions, and B, the final angular speed. Based on the information that's given, we have initial angular velocity, we have acceleration, we have time. First, we should be checking to see if everything is in its base units. You can see that our acceleration and time are, however, our angular velocity is not. So omega is equal to 40, that's rotations per minute. Okay, so we want to convert that, always get it into rads per second. So in order to do that, we are going to first get rid of those rotations. So if we have a rotation on top, we need a rotation on bottom. So for every one rotation, we have 2 pi rads. And then we want to get rid of minutes. So if we have minutes on the bottom, minutes on top, so there's 1 minute per 60 seconds. And now you can see that our minutes cancel out, our rotations and rotations cancel out, and we should be left with rads per second, which you get as 4.2 rads per second. Okay, so now let's go ahead and write out the 3 equations of angular motion. We have the first one for displacement, so theta is equal to omega naught t plus 1/2 alpha t squared. Next we have omega equal to omega naught plus alpha t. And last we have omega squared is equal to omega naught squared plus 2 alpha theta. So for part A, theta is equal to, our omega naught is 4.2 rads per second. You can see why that was so important to do that conversion, times 8 seconds plus 1/2, 1.3 rads per second squared, times our time, again 8 seconds, and we're going to square that. And we'll be left with theta is equal to 75.112 rads. There's our base units. Now it does say what is the total revolutions. Now we have to convert back. So we want to convert rads. If we have rads on top, we have rads on bottom. So there's 2 pi rads for every 1 revolution. And so if we take 75 and divide it by 2 pi, we get theta is equal to 12 revolutions. Okay, and that would be our answer for part A. Okay, next we want to find the angular speed. So it does say speed, so that's fine. We can still use our equation for angular velocity. It just means we won't really need a direction. Normally I would be asking you for velocities, displacements, or accelerations rather than just the scalar values. So we are going to take a look at, let's use the simplest of the 3, which would be equation 5. We want to find the final angular speed. So do we have the initial? Yes, we have time and we have acceleration. So we should be able to do that calculation. We have omega is equal to 4.2 rads per second plus 1.3 rads per second squared, and we're going to multiply that just by time, giving us multiplying by 8 seconds. So omega is equal to 14.6 rads per second. And since we're looking for speed, we don't need to actually give it a direction. If we were looking for a final velocity, then we would say that that would be in the clockwise direction. Okay, so that's how you would use those 3 equations of motion, very similar to how we would do our calculations for the linear, rectilinear equations of motion. So the next slide we had looked at was the relationships between angular motion and rectilinear motion, and that would be using these three equations here. So let's take a look at a problem that would end up having to use these equations. A good one to start with, as I suggested earlier, would be 1127. So let's look at 1127 in your textbook, and that can be found on page 380. So in this one it says, for the system shown below, determine the angular acceleration of the wheel and the tangential velocity at point A. Remember, tangential just means at a right angle, so that's that linear velocity that we're looking for. Okay, so here's the figure here, and we want to determine the angular acceleration of the wheel and the tangential velocity. So if you look at this, we are given a tangential acceleration. So that would be considered our linear acceleration. So we go back to the conversion equation. That says that A is equal to R times alpha. So to determine the angular acceleration, we need to rearrange this equation. So alpha is equal to A over R. So A is equal to 10 meters per second, and we're dividing by that radius arm, which makes sense because the radius arm of 2 meters, that's the full radius of this disc that is shown here, or the wheel, and it's going to the outer edge of that wheel, which is also where the A sub t is located. So we can use that. So that's 2, that'd be 2 meters. So alpha is equal to meters per second divided by meters gives you 1 over seconds. So that's where you might get confused, but just remember what you're converting. You're converting from linear dimensions, that's meters per second, and that would actually be, meters per second squared is what that should be. I was missing that originally. So now we should be getting the base units for angular units, which would be 5 rads per second squared. Okay, and that is our angular acceleration. The second part of this asks to find the tangential velocity. So this is going the other way. We already have an angular velocity of 5 rads per second, and we want to find the linear velocity. So again, using that conversion equation, V is equal to R omega. So V is equal to R omega. We want to solve for V in this case. So if we're solving for V at the outside limit of the wheel, so that means any point on the outside of this wheel, let's pick a point right at the bottom here, for example, then its velocity at that point would be equal to that radius arm, which is 2 meters, times the angular velocity, which is 5 rads per second. So V is equal to 10 meters per second. Okay. Now, with that, what I want you to also see then and be able to draw this is in which direction is velocity acting. It depends on where I take my point. Since I'm taking my point right at the bottom, directly below the rotation point, then that means that that velocity would be acting in this direction. Again, why do we call that tangential? Because it's tangential to the path. If I draw the radius arm down, we are perpendicular at 90 degrees to that radius arm. Okay, so that would be my velocity, or tangential velocity. Okay, so that is the answer for this problem. Okay, let's look at another example similar to this. We're going to look at 1140 now. For 1140, we have pulleys. So it's a set of pulleys that are fastened together. Okay, so we have 2 pulleys. The way I've drawn it's not quite concentric, but I think you get the idea here. They are fastened together, C and D, these two these two pulleys. And so that means that if D is rotating clockwise, that means C is also rotating clockwise. They're both centered at that point of rotation at the middle. We have weights A and B, which are supported by ropes, and they're wound around these pulleys. So if weight A is accelerating downwards, so we're assuming that this weight here is accelerating downwards at 2 meters per second squared. Since it is in units of linear units, we know then that is A, not alpha. So A is equal to 2 meters per second squared. We want to determine then, the following. The first part is we want to determine the angular acceleration. So angular acceleration is alpha, angular acceleration of C and D, so that's C and D. And for part B, we want to determine the linear acceleration of B, so that would be AB. So I'll go down here and show that AA is equal to 2 meters per second squared. We want to find AB. Okay, so for the first part, we want to find the angular accelerations. Again, this is a conversion problem, so if we're trying to convert between accelerations, that equation is A is equal to R alpha. We're always multiplying the angular velocity, angular displacement, or angular acceleration times the radius to get the linear term. But for this one, we want to actually find the angular value. So that means we need to rearrange this equation then. And we want to solve for alpha. So alpha is equal to A over R. Well, we are trying to find the angular acceleration of points C and D, but we're only given the linear acceleration of block A. However, since the pulley is connected physically by this rope, that means that acceleration at block A is equivalent to the point right at C. So that means that, if you were to redraw this on, or add this to our figure, is that AA would be equivalent to an acceleration there at point C. Right? That makes sense. They both are accelerating downwards at that given moment at the same acceleration. So that means that we can add the subscripts for C. So AC and alpha C. Now what we can do is we can sub in our values. So AC, which equals AA, is 2 meters per second squared over that radius arm of 180 millimeters, equivalent to 0.18 meters. And so alpha C is equal to 11.1 rads per second squared. We need a direction. Since they're going downwards, that means that pulley has to be rotating in a counterclockwise direction. So that's what it is for C. But what about for B? We don't have a linear velocity for B, do we? Although we could assume that since A is going down, B would have to be going up. The other thing, though, that's even easier than this is to remember the fact that these two pulleys are fastened together. That means their angular accelerations and their angular velocities are tied together at any point on those pulleys. So we can state that, therefore, the angular velocity of D is equal to the angular velocity of C, which is equal to 11.1 rads per second squared in a counterclockwise direction. And that's our answer for part A of this problem. Okay, next we want to solve for part B. So in this one we are actually being asked to find that linear velocity or linear acceleration at B. As I said, we know it must be going up, but we don't know what value that is. It's at a different radius arm, so it cannot be equivalent to the 2 meters per second downwards. How do we find it? Well, we do have the angular velocity, or sorry, I keep saying velocity, but angular acceleration. We know that any point on these two wheels will have the same angular acceleration. So even if we were to pick then Point B, right there, the angular velocity of that point is still 11.1 rads per second squared. And we have a radius arm to there, which is 0.12 meters. So we can use that, use that to our advantage. So AB is equal to our alpha, and that would be our alpha B, where alpha B is equal to alpha C, which is equal to alpha D, right? They're all the same, 11.1 rads per second squared. So this is equal to 0.12 meters times 11.1 rads per second squared. So AB is equal to 1.33 meters per second squared, and we need to give it a direction. So we said that is upwards. So that's our answer for part B.